Okay, so now that we've drawn the pictures of electric field, now we're going to look at a more quantitative way of calculating electric field. And here we're going to do a side-by-side comparison between gravitational field and electric field. Well, yes, we know gravity and electrostatic effects are not the same thing. There's still enough similarities that we can use what we know about gravity to help inform us about electrostatic effects. So, when we first talked about field way back, we said that field was always a ratio of force per something. The first way we defined gravitational field was gravitational force per mass, where the units were newtons per kilogram. Now, we very quickly, after doing this, proved to ourselves that newton per kilogram was the same as a meter per second squared, and when we calculated for Earth, we got 9.8 meters per second squared, which is nice, therefore showing that a gravitational field and acceleration due to gravity are the same thing. But regardless, this is how we always define a field, force per something. All right, so let's now talk about electric field. Right, so we're going to again use capital E for electric field. That's going to be our symbol. It's going to be a force per something, but which force is it? Well, it's going to be instead of a gravitational force, it'll be the electrostatic force, of course. What will the bottom be? Well, remember, the bottom was whatever the object has that allows it to experience the force. For gravitational effects, that's mass. What's the comparable quantity for electric fields? It's going to be charge. And here it is, lowercase q. This is the test charge, not the source charge. Capital Q will be reserved for source charge, lowercase q for test charge. And we're using absolute value, so this equation will just get us the magnitude. Electrostatic force is vector. For all those pictures of electric field, we're drawing arrows, so they're vectors as well, so it's going to be a vector quantity. The units come directly from the equation. This is going to be newtons per coulomb, of course. And yes, it is a vector quantity, and we're going to go right ahead and box in our new equation to calculate electric field. As always, we're going to define our terms here. So E is the electric field strength created by some other charge. And here's where it's so important. We're trying to use the same vocabulary we did back when we did gravitational fields. And remember, it's always important to know what's creating the field and what's experiencing the field. So here it's created by some other charge. We don't know what the other charge is. Sometimes we do, sometimes we don't. It doesn't matter. Whatever it is, it's not this charge. And that's what's so important. Now, this equation will get us the magnitude of that field because we're using absolute value. We don't have to worry about the sign of the charge. For the direction, well, we already know how to find the direction of the field. We just had a whole bunch of rules, 5 rules, right? And rule number 1 tells us that the direction of the field is always the direction of the force on a positive test charge. That's our convention. This is why we're using absolute value, because in reality, this charge could be negative, but that's not going to affect the direction of the field, nor will it affect the magnitude. Here's our rule, right? The arrows show the direction of the force on a positive test charge. Always we assume a positive test charge, even if in reality it's not. It doesn't matter. We don't change anything, except in the end we can show which direction the force is. But the field's direction doesn't change. Okay, Q, as I just alluded to, is the test charge. It's not the one creating the field. Ideally, it's going to be a small amount because it is a charge, so it does create its own field, but if it's going to test for the other object's field, we want it to be a small amount of charge so its field doesn't disturb the field we're trying to measure. So it's usually a small amount of charge. And again, it is not the charge creating the field. Does it have its own field? Yes, but that's not the field we're looking at. This field is created by some other charge, not the test charge. Okay, so let's be very clear. That's how we use different symbols for it. And then F sub E, that's the force experienced by the test charge. Okay, so this can be all kind of confusing, but if we relate it to gravity, we should be able to make it a little bit clearer. So let's go back to gravitational field, right? So let's say here's your mass, that's you, and this is the gravitational force you feel. What's the other name of gravitational force? We just went over this on the concepts. That's weight, okay? So here's your mass, here's your weight, and then there's lowercase g. That's the gravitational field created by the Earth, right? On the concepts page, we talk about this big idea. That's not a big idea, although if you want to make a big idea, that's fine. Just this large concept that you can never experience your own field. So this is Earth's field, right? So here's lowercase m is you. This is the force you feel because of someone else's field. That's the language we're using here. Here's some charge. Here's the force it feels because of someone else's field, right? The field created by some other charge. Okay, now, here's you. Do you create your own gravitational field? Yes, we talked about that. You do, but it's really small. Okay, so you create your own field. Is that this field? No, right? This field's created by some other object, the Earth. Okay, so go back over to here. Here's this little test charge. Does it create an electric field? Yes, it does. Is that this field? No, it is not. This is the field created by some other charge, right? Okay, so here's you. You create a field. But that's not this field, that's the Earth's field. As a result of you interacting with the Earth's field, you experience a force. That's your weight. Here's this test charge. Does it create a field? Yes, it does. Is that this field? No, it is not. That's created by some other charge. But the test charge is sitting in the field created by some other charge, and they interact with each other, so this charge feels a force, just like you feel a force. Okay? If you need to, review that, play it back over and over and over again, but as we start to do some problems, it's going to become clearer. So let's get into some problems. Let's start with number 13. Okay? So read it. I'm just going to draw some pictures, and then you're going to do some calculations. Okay. So I like to draw pictures to visualize what's happening. We know that the field is pointing down, right? So let's draw. Here's our proton. It's sitting inside a field pointing down. Now we don't know the field is uniform, but we're just going to go ahead and draw it as uniform anyway. Equally spaced. Okay? And it's pointing down. Alright, so we're going to find the magnitude and direction of the force. So go ahead and do the calculation. Alright, so we have our equation E equals Fe over Q. We're solving for force. I hope you rearrange. We always rearrange first. And so F sub E equals Q times E. Can you write it E times Q? Of course you can. I just prefer to write it Q times E. It's going to pay off dividends later on, but it means the exact same thing. Just if you could, do me a favor and write it as Q times E. Alright, now what's the charge? Oh, we're not given the charge. Oh, but wait a second. It's a proton. This is what I was talking about at the beginning of this class. That if you know it's a proton, you know its charge. By that I mean you don't have to know it off the top of your head, although after doing this a whole bunch of times you probably will. It means you could look it up. And so if you haven't already, look it up. Okay, so we know the charge, the elementary charge, and here's the field strength. To do a quick calculation, you're going to get this amount of force. But how do we know the direction? Because that's the magnitude direction. I know I gave it away here, but the direction comes back to the picture. And this goes back to rule number 1. So we're always thinking about rule number 1. You don't have to write this, just always be thinking about it, right? The arrows for the field show the direction of the force on a positive test charge. The field lines are pointing down. This is a positive test charge. It feels a force pointing down. That's it. It's always about rule number 1. So you always want to think about rule number 1. Let's take a look at problem 14. Read it, try it on your own, draw the picture, and then come back. Okay, so we know the field is pointing to the right. So I draw a field pointing to the right, and we have this charge, and it feels a force to the left. So this is the picture we draw. We don't know the sign on the charge yet. We can figure that out later. Okay, so we do our math here, we do our equation, we rearrange, right? We rearrange for Q this time. We're trying to find the charge. So Q equals Fe over E. Put our numbers in. Easy math. In fact, you know what? This is one of our metric prefixes, 10 to the negative 6, you should recognize as micro. So I'm going to rewrite it as micro. You don't have to, but it's a good idea to always remind ourselves those metric prefixes. So there's 3 microcoulombs. But it doesn't completely answer the question. It says, find the charge, but we don't really know the sign. That's shown here by absolute value. The absolute value of this charge is 3 microcoulombs, but it's not telling us the sign. So how do we know the sign? Well, it's all about the picture and rule number 1. We're always thinking about rule number 1, that these field lines show the force on a positive charge. But look at this. This charge feels a force the other way. That means it must be negative. That's how we do it. And so the actual charge is negative 3 microcoulombs. Here I've gotten rid of the absolute value because now we know the sign on the charge. So it's negative 3 microcoulombs because it feels a force opposite to the direction of the field. It's all about rule number 1. We're always thinking about that one. Alright, here's number 15. Read it, draw a picture, try it on your own, come back. Okay, so here's our negative charge. We know it's negative charge because it says so. And while most problems we neglect the gravitational force, this problem includes the gravitational force, and it's suspended, it's floating there, right? So I'm going to draw a little free body diagram. What force do we always start with in a free body diagram? Of course. And which way is the point? Of course. Hopefully you said wait, and you said straight down. Remember, it's always straight down. If you didn't say straight down, you're wrong. We've been doing this for a really long time. We always draw straight down, so there's weight. And it's suspended, it's floating there, which means there must be another force pointing which way? It's got to be up. What kind of force is it? Well, it's in an electric field, so it's got to be an electrostatic force. I'm not going to draw that field, although we could have. In fact, maybe it's a good idea to, but we'll come back to that later. Alright, so we want to find the amount of charge on the drop. So we know the net force is 0, which means these forces have to cancel out. So the magnitude of this force has to be the magnitude of the gravitational force. So we just substitute here as QE equals mg, and we're solving for the charge, so it's Q equals mg over E. And now you put numbers in. If you didn't get this far, pause the video, try it on your own. Hopefully you got this value. Now, look carefully. If you got the power of 10 wrong, it is because you did this incorrectly. Look what we're given. You're not given the mass, you're given the weight, right? You're given the weight. That is mg. So actually, you second guess yourself. If you try to multiply this number by g, you're really not reading carefully enough, right? You're given the weight, you're dividing that by the field, we should get this value. How many extra electrons does it carry? Well, maybe you have to restructure now that you maybe had the wrong number there, but we don't have to do some heavy math, although we certainly could. We've done problems like this before. We know we're going to divide this total charge by the value of the elementary charge, but we should just see this is very close to the number of the elementary charge, off by a factor of 10, so you should be able to recognize just by looking at it, it's carrying 10 extra electrons. Now the problem doesn't actually ask you to draw the electric field, but it's well worth our time. It's a good exercise here, so just pause the video, draw what direction you think the electric field is pointing. Hopefully you're referring back to rule number 1, right? Rule number 1 says the electric field shows the force on a positive test charge. Here our oil drop, our test charge is negative. It feels a force up. And so which way must the electric field be pointing? It should be pointing the opposite way, right? A positive charge would feel a force down following the field lines, but it's a negative charge that feels a force in the opposite direction. Positive charges follow field lines, negative charges go against field lines, or feel forces in the opposite direction.